10, 9, 8, 7, 6, 5, 4, 3, engine start, 1, 0, and liftoff of
NASA's Swift satellite rode to orbit aboard a Delta rocket on November 20, 2004, and is still going strong. Swift's unique instrumentation allows it to quickly locate an interesting high-energy outburst, automatically determine its position, and rapidly investigate it with ultraviolet, optical, and X-ray telescopes. Swift's versatility has led to amazing observations across a wide swath of astronomy.
A 7-year campaign to monitor the center of our galaxy with Swift has given astronomers a unique bounty. It has more than doubled the number of bright X-ray flares observed from our galaxy's central black hole and led to the discovery of a rare, highly magnetized neutron star.
Swift's primary target is gamma-ray bursts, or GRBs, the biggest and most mysterious explosions in the cosmos. On April 13, 2010, the spacecraft's Burst Alert telescope cataloged its 500th GRB.
On September 16, 2012, NASA's Swift noticed a new and rapidly brightening X-ray source. Additional X-ray behavior told astronomers that the object at the center of this activity was a previously unknown black hole.
Swift and other satellites used X-ray telescopes to monitor interactions between a pair of gigantic stars. As the stars approach each other, their fierce outflows, called stellar winds, crash together at several million miles an hour, reaching temperatures of millions of degrees and creating X-rays.
The Swift UV mosaics allow us to study the evolution of young stars in the LMC and SMC all in one view. These images are the highest resolution wide field surveys of the galaxies at ultraviolet wavelength.
On January 21, 2014, astronomers discovered an exceptionally close stellar explosion in M82, a galaxy located about 12 million light-years away. Swift's ultraviolet optical telescope imaged the brightening supernova the very next day.
When a neighboring red dwarf star named DGCVN erupted in an enormous X-ray flare on April 23, 2014, Swift caught it and monitored the eruption. The blast was some 10,000 times more powerful than the biggest flare we've ever seen from our sun.
3 unusually long-lasting stellar explosions discovered by Swift established a previously unrecognized class of GRBs called ultra-long gamma-ray bursts. Astronomers think they arise from the catastrophic death of supergiant stars hundreds of times larger than the Sun.
On March 28, 2011, Swift detected intense X-ray emission from a galaxy's supermassive black hole. Astronomers realized they were seeing the signal of a sun-like star being shredded by the black hole. Infalling gas was captured in an accretion disk and powered an X-ray jet.
A record-setting blast of gamma rays from a dying star in a distant galaxy wowed astronomers around the world in April 2013. The blast produced the highest energy light ever detected from a GRB. UV, optical, X-ray, and gamma-ray observations from Swift provided valuable data.
Asteroids crash all the time, but the effects dissipate quickly, so catching the aftermath of a recent collision in 2010 was something special. Swift's ultraviolet vision helped astronomers rule out the possibility they were seeing a comet.
A GRB so bright it could have been seen by the naked eye? That's what Swift and ground-based telescopes detected on March 19, 2008, thanks to a GRB jet aimed almost directly at Earth. Incredibly, the light from this dying star began its travels 7.5 billion years ago.
On April 29, 2009, a 5-second-long burst of gamma rays became the farthest explosion yet identified by Swift. Its light had been traveling for 13.14 billion years, placing it among the most distant objects known.
Using Swift observations, astronomers identified an abrupt slowdown in the rotation of a neutron star, an event dubbed an anti-glitch. The discovery holds important clues for understanding neutron star interiors, which contain some of the densest matter in the universe.
Swift observations, combined with theoretical research, have shown that colliding neutron stars are a likely explanation for gamma-ray bursts lasting less than 2 seconds.
NASA's Swift mission ushered in a new era of research into gamma-ray bursts. As SWIFT begins its second decade of operation, its speed, flexibility, and versatility make it an important platform for studying the most energetic and rapidly changing phenomena in the cosmos.